There is an invisible reality beneath everything you see. Most people live their entire lives believing they understand the physical world. They trust their eyes, their intuition, their common sense. But the truth is stranger than anything you could imagine. What you're about to discover isn't just physics. It's a complete revolution in how reality works at its most fundamental level. The 7 layers of quantum understanding that transform how you see existence itself. These layers aren't merely scientific concepts. They are doorways into the deepest mysteries of nature. From the simplest observation that light behaves impossibly to the most profound realization that reality itself doesn't exist until you look at it. And when you grasp these layers, something extraordinary happens. You stop seeing the universe as a machine and start seeing it as something far more mysterious and beautiful. The journey begins at the most startling point, the dual nature of light. And that's exactly where Richard Feynman himself said the entire mystery of quantum mechanics lives. Pay close attention now, because this single phenomenon contains everything strange about our universe. The first layer is the impossible duality of light, and it will shatter everything you think you know about reality. This is where physics stops making intuitive sense, where the rules you've trusted your entire life simply break down. Light is both a wave and a particle simultaneously. Not sometimes one and sometimes the other, both at the same time, always. Imagine throwing a rock into a pond. You see waves spreading outward in perfect circles. That's wave behavior. Now imagine throwing a baseball. It travels in a straight line, a solid object moving through space. That's particle behavior. These two behaviors are completely different, completely incompatible, yet light does both. When you're not looking, light travels as a wave. It spreads out, interferes with itself, creates patterns only waves can create. But the moment you try to detect it, the moment you actually look, it arrives as a particle, a tiny packet of energy hitting a single point. This isn't a theory. This isn't philosophy. This is what happens in laboratories every single day. Scientists fire single photons, individual particles of light, through to slits. And somehow, that single particle goes through both slits at once. It interferes with itself. It creates a wave pattern, one particle. 2 paths simultaneously. Your brain wants to reject this. It should. Because nothing in your everyday experience prepares you for this reality. But here's what Feynman understood. The problem isn't with nature, the problem is with your intuition. Your intuition was built for throwing rocks and catching balls, not for understanding the quantum realm. So here's how you begin to grasp this impossible truth. Stop trying to visualize it as objects moving through space. Light isn't a thing traveling. Light is a probability wave, a mathematical description of where the particle might appear when you finally look. Before measurement, the photon exists in all possible states simultaneously. This is called superposition. Watch the double slit experiment in slow motion. Study how the pattern builds up one photon at a time. Each dot appears random, but together they form the interference pattern. The wave nature emerges from countless particle detections. Let this paradox sit in your mind without forcing a resolution. Feynman himself said nobody understands quantum mechanics. The goal isn't comfortable understanding. The goal is accurate description of what nature actually does. Accept that reality at the quantum level simply doesn't behave like the world you see. Your intuition is a tool built for survival at human scales. At the atomic scale, different rules apply. Rules that seem impossible but are absolutely real. From this point forward, once you accept that particles can be into places at once, that waves can collapse into points, curiosity about what this means begins to awaken. And that opens the door to the second layer, the measurement problem. Now imagine you're watching something, but the very act of watching changes what you're seeing. Not because you're clumsy or because your tools are crude, but because observation itself fundamentally alters reality. This is the second layer, the measurement problem, where physics becomes philosophy and consciousness touches the fabric of existence. At the first layer, you learned that light is both wave and particle. But here's the deeper mystery. It's only both when you're not looking. The moment you measure it, the moment you observe it, the wave function collapses. Although simultaneous possibilities collapse into one concrete reality, before you look, the electron exists everywhere it could possibly be. It's not that you don't know where it is, it genuinely isn't anywhere specific. It exists as a cloud of probability, a mathematical wave spread across space. But the instant you detect it, that wave collapses, the electron appears at one location. The act of measurement creates reality. This drove Einstein mad. He couldn't accept that the universe was fundamentally uncertain. He believed in an objective reality that exists whether you're looking or not. He famously asked, "Does the moon stop existing when you're not looking at it?" In the quantum world, the answer is unsettling. Without observation, the moon would exist in a superposition of all possible states. Feynman approached this differently. He didn't ask what's really happening. He asked, what can we predict about measurements? And quantum mechanics gives perfect predictions. Every experiment confirms it. The math works flawlessly, but what it means philosophically remains an open question. Here's the practical path through this layer. Study the quantum eraser experiment. It shows that you can retroactively change the past by choosing whether to measure something. Now, the universe seems to adjust backward in time based on your current choice. This isn't science fiction, this is reproducible laboratory physics. Learn the mathematics of wave functions. The Schrödinger equation describes how probability waves evolve. When you measure, you apply an operator that collapses this wave. The math is precise. What it represents in physical reality is mysterious. Understand that measurement isn't just looking with your eyes. Any interaction that extracts information from a quantum system counts as measurement. Even another particle bumping into it, the universe is constantly measuring itself. Explore the different interpretations. The Copenhagen interpretation says the wave function is reality and it collapses upon measurement. The many worlds interpretation says every possibility happens in branching parallel universes. The pilot wave theory says particles always have definite positions guided by invisible waves. None of these can be proven or disproven by experiment. Embrace the measurement problem as an invitation to think deeply about the nature of reality itself. Don't seek premature closure. The mystery is the point. As you sit with this mystery, you begin to realize something profound. If observation affects reality, then time itself might not work the way you think. And that leads us to the third layer, the dimension of time in quantum mechanics. Now imagine time not as a river flowing forward, but as something far stranger. A dimension where effects can precede causes, where the future reaches backward to influence the past. This is the third layer, quantum time, where causality itself becomes negotiable. In the everyday world, time has a clear arrow. Cause comes before effect. You drop a glass and it shatters. The shattering doesn't cause the dropping. But in quantum mechanics, this simple rule falls apart. The delayed choice quantum eraser proves that decisions you make now can change what happened in the past. Here's how it works. Send a photon through a double slit apparatus. Before it reaches the detector, give it a choice. At the last moment, measure which slit it went through or don't measure. If you measure which path, the interference pattern disappears. If you don't measure, the pattern appears. But here's the impossible part. You can make that choice after the photon has already gone through the slits. Your future choice determines its past behavior. Feynman explained this using his path integral formulation. A particle doesn't take one path from point A to point B, it takes every possible path simultaneously. Each path contributes to the final probability. paths that take longer or shorter times, paths that loop backward in time. All paths are real and all contribute. This reveals something profound about time. At the quantum level, time isn't a series of distinct moments. It's more like space, just another dimension through which particles can move. The difference between past and future isn't fundamental, it's emergent. It appears only when you look at large systems with many particles. The second law of thermodynamics creates the arrow of time. Entropy increases, disorder grows. That gives us the sensation of moving forward through time. But individual quantum events don't respect this arrow. An electron can emit a photon or absorb a photon traveling backward in time. The mathematics are identical. To truly grasp this layer, study Feynman diagrams. These simple pictures show particles interacting across time. An electron moving backward in time is identical to a positron moving forward. Time symmetry is built into the foundation of physics. Watch lectures on the Wheeler-Feynman absorber theory. It suggests that waves travel both forward and backward in time, and they create the appearance of causality through their interaction. Calculate simple path integrals. See how particles that seem to take impossible routes, including routes backward in time, contribute to real physical outcomes. The math doesn't distinguish between past and future. Recognize that your experience of time flowing is real, but not fundamental. It's an emergent property of consciousness observing large-scale systems. Individual quantum events are timeless. Consider that the entire history of the universe might be determined by boundary conditions at beginning and end simultaneously. The future might be as responsible for the present as the past is. This isn't speculation, it's a valid interpretation of quantum field theory. As your mind expands to include this fluid view of time, you begin to wonder about space itself. If time is negotiable, what about the space between things? That question opens the fourth layer, the nature of empty space and the quantum vacuum. Now imagine that empty space isn't empty at all, that the vacuum is seething with energy, that particles are constantly popping into existence and disappearing again. This is the fourth layer, the quantum vacuum, where nothing is something and emptiness is impossibly full. In classical physics, a vacuum is simply nothing. Remove all matter, all energy, and you're left with empty space. But quantum mechanics reveals a far stranger truth. Empty space is filled with quantum fields. These fields never stop fluctuating. Even at absolute zero temperature, even with no particles present, the fields continue to vibrate. These vacuum fluctuations are real. They have measurable effects. The Casimir effect proves it. Place two metal plates very close together in a vacuum, quantum fluctuations push them together. Not because anything physical touches them, but because the space between the plates allows fewer fluctuations than the space outside. The pressure difference is tiny but measurable. Virtual particles emerge from the vacuum in pairs, a particle and its antiparticle. They exist for an impossibly brief moment, then annihilate back into nothing. This happens everywhere, constantly, throughout all of space. These virtual particles aren't just mathematical artifacts, they affect real particles. They change the energy levels of atoms in ways we can measure with extraordinary precision. Feynman's quantum electrodynamics describes this perfectly. Every charged particle is surrounded by a cloud of virtual photons and electron-positron pairs. These virtual particles pop into existence, interact with a real particle, then vanish. They change the particle's properties in subtle but exact ways. The calculations agree with experiments to 10 decimal places. The vacuum energy, the total energy of all these fluctuations across all of space, should be enormous. When you calculate it naively, you get an answer that's infinite. That's obviously wrong. Something is canceling most of this energy. We don't know what. This is one of the deepest unsolved problems in physics. Dark energy, the mysterious force accelerating the expansion of the universe, might be related to vacuum energy. But the calculated vacuum energy is trillions of times larger than the observed dark energy. Nobody knows why. This is called the cosmological constant problem. To understand this layer deeply, learn quantum field theory basics. Every particle is an excitation of an underlying field that fills all of space. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Study the mathematics of virtual particles. They appear in Feynman diagrams as internal lines. They violate energy conservation temporarily, borrowing energy from the vacuum and paying it back within the uncertainty principle time limit. Explore the concept of zero-point energy. Every quantum oscillator, even in its lowest energy state, retains half a quantum of energy. This is the fundamental minimum energy that can't be removed. Examine experimental evidence. The land-shift, anomalous magnetic moment of the electron, Hawking radiation from black holes, all these phenomena involve vacuum fluctuations. Contemplate the philosophical implication. If empty space is full of energy and activity, then nothingness doesn't exist, something is the natural state. This vacuum, this seething ocean of virtual particles, is the substrate of reality itself. When you grasp that space itself is alive with quantum activity, you're ready to understand how particles can affect each other instantly across vast distances. That's the fifth layer, the most shocking prediction of quantum mechanics. The phenomenon Einstein called spooky action at a distance, entanglement. Pay attention now, because this is where quantum mechanics becomes genuinely inexplicable, where even the mathematical formalism doesn't hide the weirdness. The fifth layer is quantum entanglement, where separate particles share one identity and information travels faster than light without traveling at all. Create two particles in a way that links them. Measure one particle and you instantly know something about the other particle, even if that other particle is on the opposite side of the galaxy. Even if there's no time for a signal to travel between them. They remain connected through what Feynman called the quantum amplitude, a mathematical entity that describes both particles as a single system. This isn't like identical twins who share similar properties because they came from the same source. Entangled particles don't have definite properties until you measure them. Before measurement, neither particle has a specific spin direction. They exist in superposition, but they're correlated superpositions. When you measure one and it collapses to spin up, the other instantly collapses to spin down. Einstein tried to prove this was impossible. He proposed the EPR paradox. Either quantum mechanics is incomplete and particles have hidden properties we can't see, or information travels faster than light, which violates relativity. He was sure quantum mechanics must be wrong. But John Bell developed a mathematical test. Bell's inequality shows that no local hidden variable theory can reproduce quantum predictions. Experiments have been performed thousands of times. Quantum mechanics wins every time. The correlations are stronger than any local realistic theory allows. The particles aren't sending signals to each other. That would violate relativity. Instead, they're not truly separate. They're parts of a single quantum state that spans space. Distance is irrelevant to this connection. The universe at the quantum level isn't made of separate things interacting. It's made of holistic states that defy spatial separation. Feynman emphasized that you can't use entanglement to send information faster than light. When you measure your particle, you get a random result. Only when you compare notes with someone measuring the other particle do you see the correlation. That comparison requires classical communication, which can't exceed light speed. But the correlation itself is instantaneous and real. Change happens simultaneously in both locations the moment measurement occurs. Not because a signal traveled, but because the wave function was never really divided by space. To master this layer, study the EPR thought experiment in detail. Understand exactly what Einstein found troubling and why he was both right and wrong. Learn about Bell's theorem, work through the mathematical inequality. See how quantum mechanical predictions violate it and why this matters. Examine experimental tests. The aspect experiments in the 1980s, more recent loophole-free tests. Every experiment confirms quantum mechanics and rules out local realism. Explore quantum teleportation. Using entanglement, you can transfer a quantum state from one location to another without the state ever traveling through the space between. This is real and has been demonstrated many times. Consider the implications for the nature of reality. If particles that have never interacted can be instantly correlated across any distance, then space as a separator of things is an illusion. Everything might be entangled with everything else at some level. The universe might be fundamentally holistic. As you absorb the reality of entanglement, you begin to see that the quantum world isn't just weird. It's useful, profoundly useful. That realization opens the sixth layer where quantum strangeness becomes quantum technology, where understanding transforms into invention. Now imagine harnessing the impossible for practical purposes. Building computers that calculate using superposition. Creating unbreakable encryption using entanglement. Measuring with precision beyond classical limits. This is the sixth layer, quantum technology, where the strange becomes the revolutionary. Quantum mechanics isn't just abstract theory. It's already the foundation of our technology. Transistors work because of quantum tunneling. Lasers work because of stimulated emission, a quantum process. MRI machines use nuclear magnetic resonance, a quantum phenomenon, but we're entering a new era. Technologies that exploit quantum effects deliberately and systematically. Quantum computers are the most famous example. Classical computers store information in bits that are either 0 or 1. Quantum computers use qubits that can be 0 and 1 simultaneously through superposition. A quantum computer with 300 qubits can represent more states simultaneously than there are atoms in the universe. This doesn't make quantum computers universally faster. For many tasks, they're no better than classical computers. But for specific problems like factoring large numbers, simulating quantum systems, or searching databases, they're exponentially faster. A problem that takes a classical computer billions of years might take a quantum computer hours. The challenge is decoherence. Quantum states are fragile. Any interaction with the environment destroys superposition. Quantum computers must be isolated completely, cooled to near absolute zero, shielded from all vibration and electromagnetic radiation. Maintaining coherence long enough to complete calculations is the central engineering challenge. Quantum cryptography offers provably secure communication. Send a secret key using entangled photons. If anyone intercepts the photons to read the key, they inevitably disturb the quantum state. You detect the disturbance and know the channel is compromised. This isn't security through complexity like classical encryption. It's security through fundamental laws of physics. Quantum sensors achieve precision beyond classical limits. The Heisenberg uncertainty principle sets fundamental limits on measurement. But using squeezed light and entangled particles, you can redistribute that uncertainty. Measure one property with extraordinary precision by accepting more uncertainty in another property. Gravitational wave detectors use these techniques. Feynman predicted quantum computers in the 1980s. He realized that simulating quantum systems on classical computers is impossibly hard. The amount of classical information needed to describe a quantum system grows exponentially with system size. But a quantum computer is itself a quantum system. It can simulate other quantum systems naturally. To engage with this layer practically, learn about current quantum computing approaches. Superconducting qubits like IBM and Google use, trapped ion qubits like IonQ uses. topological qubits that Microsoft is developing. Each approach has different advantages. Study quantum algorithms, Schur's algorithm for factoring, Grover's algorithm for search, quantum simulation algorithms. Understand not just what they do, but why quantum mechanics enables them. Explore quantum cryptography protocols. B84, E91, quantum key distribution networks already deployed in several countries. Follow developments in quantum sensing, atomic clocks accurate to 1 second in billions of years. Magnetometers sensitive enough to map brain activity. Gravimeters that can detect underground structures. Try programming a quantum computer. IBM offers free cloud access to real quantum computers. Learn the basics of quantum gates and circuits. Run simple algorithms and see how quantum behavior enables new computational possibilities. Recognize that we're at the beginning of a technological revolution based on controlled quantum effects. The next decades will see quantum technologies transform computing, communication, sensing, and simulation. Understanding the physics positions you to understand and potentially contribute to this revolution. When you see quantum mechanics not as abstract weirdness, but as the foundation for transformative technology, you're ready for the final layer. The deepest question of all, what does quantum mechanics tell us about the nature of reality itself? That's the seventh layer, interpretation and meaning. Now imagine standing at the edge of human understanding, peering into the philosophical abyss that quantum mechanics opens. You've learned the phenomena, understood the mathematics, seen the applications, but what does it all mean? This is the seventh and final layer, quantum interpretation, where physics becomes metaphysics and science confronts the limits of explanation. The mathematics of quantum mechanics is clear and precise, the predictions are perfect. But what the mathematics represents, what's actually happening in reality, remains disputed a century after the theory's creation. Multiple interpretations exist, each consistent with experiments, each leading to radically different views of existence. The Copenhagen interpretation, developed by Bohr and Heisenberg, says the wave function represents our knowledge of a system. Measurement updates that knowledge by collapsing the wave function. Reality exists in a definite state only when observed. What happens between observations is meaningless to ask about. Shut up and calculate, as the saying goes. The many worlds interpretation, proposed by Everett, says the wave function never collapses. Every quantum possibility happens, but in separate branching universes. When you measure a particle's spin, the universe splits. In one branch you see spin up, in another branch you see spin down. Both outcomes are equally real, you just can't access the other branches. The pilot wave, or de Broglie-Bohm interpretation, says particles always have definite positions. They're guided by a real physical wave that evolves according to Schrödinger's equation. The randomness in quantum mechanics comes from unknown initial conditions, not fundamental indeterminism. This is a deterministic, realistic theory that reproduces all quantum predictions. Quantum Bayesianism or cubism treats quantum states as subjective degrees of belief, not objective properties of reality. Different observers can assign different quantum states to the same system, just as they might have different probabilities for a coin flip. Measurement updates your beliefs, not reality itself. Feynman himself avoided interpretation questions, he focused on calculation and prediction. When asked what quantum mechanics really means, he often replied that nobody understands it, so don't worry about it. Just learn to calculate correctly, yet even he acknowledged the profound weirdness. He said, if you think you understand quantum mechanics, you don't understand quantum mechanics. But ignoring interpretation has costs, it leaves fundamental questions unanswered. Does reality exist when nobody's looking? Do we have free will if the future is determined by wave functions? What is observation and why does it seem special? These aren't idle philosophical musings. They're questions about the nature of existence that physics has forced upon us. The measurement problem remains unsolved. Why does the wave function collapse? What counts as a measurement? Where exactly is the boundary between quantum and classical? Some physicists think consciousness is involved, others think it's just complexity. Still others deny the problem exists because nothing collapses in their interpretation. To engage deeply with this final layer, read about the major interpretations carefully. Understand that each is consistent with all experimental data. The choice between them isn't scientific but philosophical. Study the measurement problem from multiple angles. Decoherence theory explains how quantum systems become effectively classical through interaction with their environment but doesn't fully solve the measurement problem. Examine the role of information in quantum mechanics. Some physicists think information is more fundamental than matter or energy. John Wheeler said it from bit, reality emerges from information processing. Consider the relationship between consciousness and quantum mechanics. Some interpretations suggest observation requires consciousness. Others treat observation as any physical interaction, neither can be ruled out experimentally. Explore quantum foundations research, active experiments testing different interpretations. Tests of collapse models, searches for deviations from quantum mechanics. Attempts to unify quantum mechanics with general relativity in a theory of quantum gravity. Think about what it means that reality at its foundation defies human intuition. Our brains evolved to catch prey and avoid predators, not to understand atomic reality. Perhaps genuine understanding is impossible. Perhaps we can only master the mathematics and make accurate predictions. Or perhaps the weirdness itself is telling us something profound. That the universe is participatory, that observation is creative, that consciousness and reality are intertwined, that the boundary between self and world is less clear than it appears. Feynman said nature has a great imagination, far greater than ours. Quantum mechanics shows us that reality is stranger, more subtle, more beautiful than we ever imagined. The electron doesn't take one path or the other. It takes all paths. The particle isn't here or there. It's everywhere until you look. Time doesn't flow forward. It's just another dimension we move through. These 7 layers, from the duality of light to the interpretation of reality itself, form a complete journey through quantum understanding. You begin with confusion about waves and particles. You end with profound questions about existence. You started with phenomena that violate intuition. You finish with a transformed conception of what reality means. The genius isn't in memorizing quantum facts. It's in learning to think quantum mechanically, to hold multiple contradictory ideas simultaneously, to calculate without demanding visualization, to accept mystery without abandoning rigor, to know that reality is far stranger than your senses suggest. Feynman revolutionized physics not by making it simpler, but by teaching people to be comfortable with its difficulty. He showed that genuine understanding means accepting what nature shows you, even when it contradicts everything your evolution prepared you to expect. The quantum world is the real world. The classical world is an approximation that works at human scales. When you've journeyed through all 7 layers, you realize quantum mechanics isn't just a theory in physics. It's a revelation about existence itself. You're not here by accident. You're here because you want to understand reality as it truly is, not as it appears to be. And that curiosity, that willingness to have your intuitions shattered and rebuilt, that's the first sign of a scientific mind ready to grasp the deepest truths nature has to offer.